Hey guys, this is video 14.7. We're going to be talking about voltaic or galvanic cells in this video. This is something that you will see show up on your Regents exam, so make sure you really spend the time practicing this and answering the questions about it. I've got extra practice with it. This also may be a video you need to watch a couple of times to really understand the ins and outs of the cell itself. Okay, kind of what's going on, what's changing, and things like that. So really make sure, again, flashcards are a good thing to use and to make to kind of help remember the big pieces of this, because last year's Regents exam and a lot of them in the past, you had to draw a picture or label the picture as to what's going on. So let's jump right in. These are cells that spontaneously, so when you hear that word, guys, spontaneously, what should you be thinking? You should be thinking, hey, I'm going to be using table J. All right, I've got to look at it. They spontaneously convert chemical energy into electrical energy or current, or electric current. So the best example of these are batteries. Now there are two types of batteries that we are going to talk about, two types of different cells, but we'll get into those in a little bit later. So let's kind of talk about the nuts and bolts as to what's happening, and then I'm going to have this picture. I know it's a small picture. You know, I can get you a bigger one diagram if you want to kind of use that and you know, relabel things so it's a little bit bigger. But yeah, I realized that after I printed all your stuff that this was the picture, so it'll be something I got to go back and redo. So the cathode. Okay, the cathode is the less active metal of the two that you're given. So again, how we find out it's less active, we're going to use table J, right? It's lower on table J. Because it's less active, it's going to spontaneously, it's the key word here with voltaics, guys, is they are spontaneous, spontaneously attract electrons, all right, to it. This is going to be the positive electrode in a voltaic cell. Again, we're talking about voltaic cells here specifically. It may not be the same case in the next video when we talk about electrolytic cells. This is also the electrode where reduction occurs. And if you remember to our last video where we did the basics, right, that saying red cat, right, reduce cathode. Now think to yourself, okay, what's happening to get reduction to happen? Well, GER, right? Gain electrons reduce. Now that may, in your mind, you might be thinking, well, how in the world is that possible that if you're gaining electrons that it's going to be the positive electrode? Well, let's take a look here at this diagram, okay? What's actually happening, okay, here we go. Here's our cathode. So in an voltaic cell, you have two half cells. So you see how this dotted line here is in the middle? That's a separator. Okay, it could be a separator like that, or it could be a salt bridge. So it could be something kind of going over like this, which is what we're going to use in our lab when you guys get there. So they are separated somehow. Okay, so we're talking about this half cell where the cathode is. Okay, well, the reason why it's positive is you can see kind of what's taking place. All right, you've got all these positive ions. So we've got a cathode. Let's say, for example, the classic is kind of copper. All right, so you've got also in a copper solution that has positive ions. Well, the electrons are flowing to it. Okay, so it's attracting the electrons. As you can see, these blue dots that are coming in here. Well, what are negative electrons going to do? They're going to start drawing in the positive ions from the solution. Okay, that's how it becomes the positive electrode, because it's drawing all these positive charges that will actually start to plate on to that metal. So if this is a strip of metal here, it's going to start getting bigger. The mass of our cathode is going to increase. So it's going to gain mass, all right, because all these ions coming out of solution are going to start plating on that electrode, okay? So we'll come back and talk more about that in just a second. Let's go back and talk about the other side, which is the anode. The anode, guys, as you might think, is going to be opposite of the cathode. So if the cathode is the less active of the two metals, the anode is going to be the more active. Again, table J, higher up on table J. This is going to spontaneously, meaning without any extra energy, spontaneously lose electrons, all right, to the cathode. So remember, the anode gives its electrons away to the cathode. That's always going to hold true. The flow of electrons is always from anode to cathode. We're going to star that right here. Electrons flow anode to cathode. All right? Doesn't matter what type of cell you have. So the anode here, guys, is going to be the negative electrode in a voltaic cell. This again is where oxidation is occurring. Our saying from our last video was an-ox. Okay, so let's take a look. Let's think about why. How is that going to be negative? If it's giving its electrons away, how is it negative? Well, you kind of just answered your own question right there, is because all of those negatives within it. Now the other way, okay, too, again, so electrons are going to be flowing from the anode to the cathode. So the electrodes are going to go like that. That's going to be one question you're probably going to be asked on the Regents. Which way do electrons flow in a voltaic cell or in an electrochemical cell? It's always anode to cathode. So you've got all these negative charges right here, right, that they're just giving away. So the electrons are flowing, which then gets the electricity flowing. Okay, so what tends to happen with the anode, let's say, for example, the classic example is zinc, which is like what you're doing in your lab. All right, so zinc, sorry, it's zinc metal. And then once they get rid of their electrons, okay, which is why it's negative, you got all these electrons spontaneously getting rid of, the zinc starts to fall into solution as ions. Okay, it starts forming those ions. Okay, so this is actually going to get smaller. They will tend to lose a little bit of mass. Now you might be thinking, how can something gain mass and something lose mass? Well, that's where this salt bridge comes into play. All right, and I'm going to actually kind of make this salt bridge purple. Okay, this is our salt bridge. And that plays a very important role on a number of different reasons why. Without the salt bridge, guys, the two cells could not be connected to each other. So that means all these electrons couldn't continuously flow. So a salt bridge typically has something like maybe, sodium sulfate as the salt in there that allows for these electrons to keep flowing. Because you might think, well, if all these electrons are flowing over here, you're getting all these positives on the left side where my cathode is, and then they're going to stop. Or why would it, start giving up, keep giving up these electrons over here if you get all these zincs that are positive in the solution? So guys, inside of these cells, you've got solutions, liquids, all right, where you have all this extra ions. So if you have a copper piece of metal, you're going to have a copper solution. If you have a zinc piece of metal, you're going to have a zinc solution down here, or it's going to become a zinc solution, and that's going to allow electrons to keep flowing. That's what the salt bridge does. Okay, so that you have positives and negatives that keep flowing through this salt bridge that allows for the circuit to be complete. So it keeps going around in a circle to where it's starting to, keep flowing, and so you don't get that charge buildup. All right. So if we take a look at the redox reactions for each, kind of the half reactions, all right, our cathode, we said was those electrons were flowing through it, so it's reducing. Okay, so you have those ions in solution, those Cu2 plus ions, and they're gaining the electrons that are coming from the anode. So that's producing that copper metal. That's why it's gaining mass, because now you're making solid copper from those ions that were in solution when the electrons come and attract to it, and it's undergoing that redox reaction, that half reaction. On the flip side, why you're losing mass with the anode is because zinc is going from solid zinc, giving up its electrons and becoming ions. So these ions from the zinc are going to start to fall off. Once they lose it, they're no longer solid, and that's why they go into the solution. So that's why it will tend to lose a little bit of mass. Now, if you think about the reaction overall, right, law of conservation of matter and mass, the whole system, guys, is not losing mass. It's just being transferred from one place to another. Okay, the electrodes themselves are maybe gaining mass or losing mass, but the overall mass in the entire system is still staying the same. All right, now I know that's a lot of information. Guys, you've got to know the different parts, and by doing extra practice, and I've got lots of it, that's where you're going to kind of really understand it. So flashcards are going to be a huge help for you as well to keep all that information straight. Now, let's talk about specific examples of where we use these voltaic cells in everyday life. So the first example is called a wet cell. This would be found in car batteries, where it literally is, like it says, is wet cell, like it's wet, like there's liquid involved. All right, the cell that you're going to make in lab is a wet cell as well. Car batteries, they are made kind of a form of lead storage batteries. They consist of a lead anode and a lead oxide cathode. Again, specifically 2 car batteries, not necessarily all wet cells are this way. Both of the electrodes, guys, in a battery, in a car battery, are submerged in sulfuric acid. So the advantage of this process is that it's reversible. We'll talk about how it's reversible in the next video. In a car, it's reversible using an alternator. And again, next video we'll talk more about that. The disadvantage, though, to these batteries are they are very heavy. If you've ever had to change a car battery, you're going to notice that, hey, they weigh a good amount. They're also dangerous, specifically when they start to corrode. So this is a good public service announcement for you to make sure that if your terminals on your battery are corroded, clean them out. There's tools you can use. You actually can clean them with Coca-Cola. But anyway, so that's first example is a wet cell. And then the other one, the more common battery that you'd be thinking of, are dry cells. And these are the batteries that you use kind of more regularly that aren't necessarily reversible. Now, if you have a rechargeable battery, yes, there's other chemistry involved to get them to be recharged. But these are your like alkaline batteries, guys, that you buy for your remote controls, your radios, anything like that. All right, where instead of being wet, there's a paste. Okay, that gray stuff in this picture is a paste. It's still an electrolyte paste that allows the electrons to flow. You still have a separator, which is like your salt bridge, that's in there, but it's a little bit different. So we're not going to get into that too specifically. Here's the key, guys. You need to make sure you know this for the reagents, is what the purpose of a salt bridge does. And that provides a path for the flow of electrons, okay, between the 2 half cells. So without that salt bridge, the circuit's not complete and it wouldn't work. Okay, there's not going to be any flow. This also prevents the buildup of charge. Like, again, we talked about in the video, right? You get all these positives over here on one side and the negatives more on the other side. So when we think, well, what's going on? Why, wouldn't that build up? That's the salt bridge. It keeps from that buildup of charge. Make sure you know these 2 answers. They appear all the time on every Regents exam, so make sure you know those. Now, again, you may have a lot of questions. I may have went too quickly. Go back and rewatch it. Do practice in class. Don't rush through this because, again, you're going to see questions on the Regents dealing with this. Until next time, I'll see you later.